micro-VMs. So I'm sure a lot of you have seen this comic before. And the good news here is that this is much less of a pain point with Bazel. My builds are much faster now. Has Bazel completely fixed all of my productivity problems? Not quite. I'm guessing that this version of the comic is just as relatable for a lot of you. So a situation that I frequently find myself in is I've just finished some code and pushed it to GitHub. And before I add reviewers, I figure that I should probably wait for CI to complete. But of course, it's running kind of slowly. And so I peek down at my phone. But that, of course, completely drags me in, and I end up spending more time than I intended. And by the time that I look up, I realize that CI has failed, maybe due to a linting failure. So I fix one line of code, repush, CI starts again. This time I might wander to the kitchen for a snack. And eventually I wander back to my laptop, realize that CI has failed again, this time due to a unit test failure. And so on this process goes, dragging on for a lot longer than it probably should. So this has led us to an important question that I'm sure lots of companies also face. How do we make our CI workflows fast every single time? Using Bazel in your CI pipelines is a really good first step. So a good CI pipeline will minimize build times and compute resources. It'll let you run jobs in parallel, and if a single job fails, it'll fail the entire pipeline, so you're not wasting any resources. And if this sounds familiar, it's because that sounds a lot like a build system. And these problems are exactly what Bazel was meant to solve. But if you're anything like me, you might have a pretty short attention span. So what if you need your CI to be blazing fast? Unfortunately, even with Bazel, even with remote cache and RBE, your CI might be slow. Preparing a CI runner to execute a workflow takes time. It has to build or pull the image, clone the Git repo, and once the Bazel build has started, Bazel has to do the analysis phase and make network requests to the cache. And the analysis phase has been a particular pain point for us at BuildBuddy. For large repos, this can take several minutes, and it's especially tricky to preserve because it lives completely in memory. Here's a sample CI run. From a Bazel standpoint, this run was actually pretty successful. You can look at the cache tab and see that there were a lot of cache hits. And building and running our entire test suite took 6 minutes, which isn't bad. But here, you can see a lot of the inefficiencies that I mentioned. You can see that we have to clone the Git repo, and the first time we run the Bazel command, we have to download it and start the local Bazel server. And the analysis phase takes 1.5 minutes. For a 6-minute build, this is 25% of the entire build time. You know that really satisfying feeling where you rerun a build on your local machine, and the second time it's basically instantaneous? Well, we wanted to build that for CI. So we decided that we would clone our CI runners. So after we've done the slow work of preparing a CI runner once, we wouldn't have to do it again. New CI workflows will be assigned to cloned machines that have warm Bazel instances. And this worked. This approach helped us save several minutes per CI run. Now, the majority of our CI runs complete in just seconds. We saw an 8x reduction in the median duration of our CI runs. And something really important to call out here is that this is compared to other workflows that are also using Bazel. So our baseline is using Bazel with remote cache and RBE on GitHub runners. So our CI pipeline was already fast, and we were still able to make it 8 times faster. This graph helps visualize the performance benefits of our cloning approach. So we call our CI product BuildBuddy workflows, and you can see it on the left in the teal. And you can see that the majority of our BuildBuddy workflows complete in 30 seconds or less, while basically the fastest run on a GitHub runner takes 2.5 minutes. Here's another example CI run, but this time it was assigned to a cloned machine. You can see that we don't have to install Bazel or clone the Git repo, and the analysis phase is much faster. So remember the first time, the analysis phase took 1.5 minutes. This time, it doesn't even take a second. And the total build time is only 9 seconds, which is way faster than the 6 minutes that we saw before. So in order to implement this, we use Firecracker, which is a virtualization technology created by AWS. And we chose Firecracker for a few key reasons. First, we liked that it's been battle tested by AWS Lambda, which reassures us about its stability and its scalability. Firecracker also provides really strong isolation and security guarantees. So this was important for us because we run CI for multiple companies on the same executors. Firecracker micro-VMs are also lightweight. While a normal VM might take a couple seconds to boot up, a Firecracker micro-VM can boot up in just a couple hundred milliseconds. And another important feature is that VMs have a lot more functionality than containers. So anyone who's ever tried to run Docker in Docker knows that that is extremely painful. Running a container inside of a container is really hard. But a lot of companies have complicated Docker setups in their CI. And so we wanted to make sure that we could support that easily and that people would be able to easily configure their CI runners by bringing their own Docker image. And running a Docker container in a Firecracker VM is much easier. Another really cool feature of Firecracker is the ability to snapshot. A snapshot lets you capture the entire state of a running VM, including both the disk and the memory. So when you load that snapshot onto a completely different VM, which is a completely different machine, it'll have the exact same state, including that hot Bazel cache that we want to preserve. Another cool feature of snapshots is it lets you serialize VMs to disk. So let's say you wanted to reuse a Docker container. You could pause it and resume it, but the paused Docker container would still have to run in the background, which continues to use memory and CPU. And these are much more expensive resources than disk. Disk is also much more resilient to host machine restarts, and the contents are shareable across the network. So there's really no way that you can transfer a paused Docker container over the network in the same way that you can transfer a file. So let's imagine a sample CI run. When the workload comes in, you have to start the micro-VM, build or pull the image, clone the Git repo, and do that expensive analysis phase in the build. Let's say this takes 6 or 7 minutes, even with Bazel. Now let's imagine a second CI run is triggered. Even if this is assigned to a completely different executor, with our cloning strategy, it'll be much faster. We can load the snapshot, but now we no longer have to prepare the build because it's already on the machine. And syncing the Git repo and the analysis phase and the build are significantly faster. So like in the example I showed before, this could be something as fast as 10 seconds. But of course, performance improvements this good can't come too easily. And there were definitely some pain points with Firecracker snapshots out of the box. Snapshot files are really large. A single disk snapshot can be over 20 gigabytes. And this makes them expensive to transfer, copy, or even just write. We literally had to run 4 times as many local SSDs just to handle the writes initially. And this makes them really hard to efficiently reuse. It was too expensive to create a copy of the entire snapshot file, so we made the snapshot files mutable. If a cloned VM wanted to use a snapshot, it would directly write to it. And I'm sure, as you can imagine, that approach is not scalable at all. That means that only one cloned VM can start from any given snapshot at a time, because if multiple VMs were using the same files, they would clobber each other's changes. So if you have any additional CI workloads greater than the number of snapshot files available, the additional workloads would have to start on slow, clean runners. And in practice, it wasn't actually feasible to share these snapshots over the network because they were too big. So during executor scale-ups, all workloads that were assigned to the new machines would have to start on slow, clean runners because these new machines didn't have the snapshot files locally. Another problem we faced was we frequently had to throw away our very valuable snapshots, and this would exacerbate this clean runner problem. To be safe, if one of our CI runners had an error, we would just throw the snapshot away because we didn't want to risk corrupting CI runs that could get assigned to this snapshot. But this problem was especially bad during executor restarts, which would break the running task stream and generate errors. So when we had a machine restart, we would essentially throw away almost all of our snapshots, making all subsequent CI runs a lot slower. And machine restarts can happen at any time, whether from deployments or automatic Google Node upgrades. And in a lot of situations, we actually like that we can treat our executors like any other resource that we can spin up and throw away at will. And you would want your system to be fault tolerant throughout that, and ours just wasn't. So we wondered, what if we could split our snapshot into more manageable chunks? Then we could store them in a remote cache that would be much more resilient, and we could do cool things like compress the chunks for even more efficient storage. The problem is the kernel expects disk and memory to look a certain way. So if you attach a disk to a VM, the kernel expects the disk to be there. The kernel wasn't built to do fancy things like serve compressed blocks from a remote cache. So we realized that if we wanted to do cool things like clone VMs over the network, we would have to implement this ourselves and manage disk and memory access. Then we could store the backing data however we wanted. So we introduced userfaultfd to handle memory access and Fuse to manage disk access. As a quick memory review, when a process requests memory, the kernel assigns virtual memory to it. So while the process treats this like data that lives in RAM, it isn't actually guaranteed to live there. Often the underlying data will live on disk, and this abstraction was created because it lets processes use more memory than the physical limits of a more expensive RAM chip. When a process tries to access a virtual memory page that hasn't been allocated, it triggers something called a page fault. And this is where the kernel goes to disk and actually copies over the underlying data into memory where the process expects it to be. So let's take an example. We have VMA with a warm Bazel instance, and we take a snapshot of it. So this dumps this massive snapshot file into disk. Now, when we have a cloned VM trying to access its memory, this will trigger a page fault. Control is transferred to the kernel, which will then go to disk and bring the data from disk into RAM, and then resume the original process in the VM. By default, the kernel handles page fault. Userfaultfd is a technology that lets developers handle page faults in user space. So this lets you define custom behavior for how your memory is loaded. And that would let us serve memory blocks from a remote cache or add any custom implementation that we wanted. This is the exact same diagram that I showed before. I've just replaced the kernel with the userfaultfd handler. So in this situation, the UFFD handler is responsible to going to the disk and copying over the relevant data to memory. But because this is user implemented, we now no longer have to hold the assumption that the underlying data lives on disk the way that the kernel expected. We can now replace this with our caching layer. So we can split up our snapshot into smaller, much more manageable chunks and store them in a remote cache. And this flexibility gives us a lot of power. For example, we can compress the data, and it also minimizes data duplication and lets us utilize our powerful caching nodes, which are optimized for data transfer in a way that our executors maybe weren't. It's also much more scalable. So even if we were somehow able to share our local snapshot files on disks, at most a couple VMs or different machines would be able to access it at any given time. But with a remote cache, we can have an infinitely scalable set of VMs trying to fork from the snapshot at any given time. And these VMs can be on completely different machines, letting us reach our goal of cloning VMs over the network, which is pretty cool. On the disk side of things, we use Fuse, which stands for File Systems in User Space. So just like how UFFD lets us capture memory reads and writes, Fuse lets us capture disk reads and writes. So the overall architecture looks about the same. The way that you set it up is just a little different. We can mount any number of Fuse-backed disk images to empty directories on the VM, and it'll just treat them like any normal disk. And when the VM is trying to access the disk, instead of transferring control to the kernel, which would go to the disk, the kernel will transfer control to a Fuse server. The Fuse server can then be configured to call callback functions that are user implemented. So this is where we can implement our custom caching code. And the flexibility that we get from UFFD and Fuse is really exciting because it unlocks all of this future optimization work. So for example, we can be more efficient in how we chunk our snapshot files. Right now, we just split the snapshot files into equal-sized chunks, but we can use something like content-defined chunking to be smarter in how we break them down, which lets us minimize data duplication even more. We can also be smarter in how we match an incoming CI workload in a snapshot. So you can imagine we can use something like creation time or whatever. And so even if we've never built a commit before, we can try to match it to a snapshot that will minimize build times as much as possible. And we'll also be able to dynamically save snapshots in the background. So right now we have to wait for the VM to finish execution, and then we serialize the entire thing to a snapshot, which can be slow. It can take a couple seconds. But with something like userfaultfd write protection, we can capture writes as they happen and dynamically update the remote cache chunks. Yeah, so a lot of hard work has gone into this. So I thought I would finish off my presentation with a little demo. So here I'm triggering a CI workflow from the command line with our execute workflow API. And you can see that this is for the build buddy repo, and we're running the test action, which builds and tests our entire test suite. So here I'm copying the invocation ID so that we can view the CI run in our UI. You can see that this takes a little time because we have to prepare the CI runner. And we're doing a lot of that setup work that I mentioned before. So we're cloning the Git repo and all this other stuff. And at this point in the demo, you might be a little bored. And this is probably where you would start to get bored in a normal CI build as well. So this workflow ended up taking 6 minutes and 2 seconds. Here, I run this same workflow again, but this time it gets assigned to a cloned runner. So you can see in the logs at the top, it says syncing existing repo, showing that we did in fact get assigned to a cloned runner. And you can see that the build has already completed. And this time, the build only took 20 seconds. So the good news is that if you want to take advantage of all of our hard work, you can use our workflows product. And the basic version with out-of-the-box Firecracker is already live in production. And while this version isn't perfect for some of the reasons I mentioned, it's still pretty good. And we were able to significantly speed up our CI with this. In most cases, our CI runs were still completing in seconds. And we just launched our over-the-network version with Fuse and UFFD and Dev. So hopefully that makes it to prod soon. And something cool about our workflow product is it's easy to integrate into pre-existing CI pipelines with that execute workflow API that I used in my demo. So if you don't want to migrate your entire pipeline, hopefully this makes it a little smoother. But also, if you don't want to use our product, we completely understand. And all of our code is publicly available on GitHub. So if you're curious or you want to try and roll your own, we encourage you to check it out. It's pretty gnarly, but pretty cool. And of course, Slack us with any questions. Yeah, so finally, just wanted to shout out the Build Buddy team, and especially Brandon, who I primarily worked on this with. Does anyone have questions?
Yeah, hello, thanks for the nice talk. I wondered if you write into the snapshots while the VM is down. Doesn't that lead to unexpected results? I guess, I mean, like usually if you run on an operating system, you wouldn't expect the disk to instantly change like below you. And I guess that would kind of feel like that from the point of the VM.
Yeah, you mean if we're like dynamically capturing the writes, how that will affect future runs?
No, I meant like for the old version where you basically, after the run, write to a snapshot image. And then, as I understood you, while this is called, you actually mutate that image to update it to a new state. And then you start a new VM from that. And I just wondered how to make that safe, because it sounds interesting for other things.
Yeah.
But I wondered if that isn't problematic.
Yeah, so we would, when we pull down the snapshot, we have a local version of all of the chunks, and we have copy on write implemented to ensure that writes from other VMs won't clobber the snapshots that other VMs are already using. Is that answering your question? Sorry.
Not really, but probably it's too complicated. I think this is already the new version, right? But okay, I think near me there was like another question.
Yeah, perhaps a bit related to that. I was kind of curious, did you have a look at using copy on write file systems like, or file systems with built-in copy on write capabilities like ZFS, or I think ButterFS has it too, for this problem?
Yeah, we did. And right now our VMs are using the ext4 file system, which doesn't inherently support copy on write. And so we were considering whether we should just migrate file systems or just consider another approach. And we ended up deciding to just implement it ourselves because of all of the additional flexibility it lets us have.
And one perhaps related question, like how are you actually running these? Are these Firecracker VMs running in a nested virtualization context, or are you running these on bare metal hosts?
They're running on bare metal hosts. Yeah.
Thank you. Mm-hmm. Very interesting talk.
Okay. So first of all, I think it's super impressive that you guys implemented UFFD. I'm already like implementing Fuse is like, oh, okay, cool. But like, I guess you have your own kernel module or something for UFFD. And yeah, I think this is like real engineering. I really love that.
Thank you.
Although I do want to zoom a little bit out, and if I understand correctly, basically what you guys are doing, you ensure that your Bazel server is like a long-running process, and you don't have to pay all the time for the restarting this process and do the analysis. How do you handle different build configurations for the same CI jobs?
Yeah, so in our snapshot key, we hash the configuration. So if you have a different configuration, you would get a completely different snapshot.
Okay, so it comes out of the box. It's not.
Yeah.
Cool.
Maybe it's a clarification question first, but So you said, if I understood right, you have sort of a base VM run, and then you snapshot that and you replicate it to generate multiple runners. And then if those run in parallel, they're going to generate separate state. Do you end up merging this state back into one, or how do you decide which of those becomes the basis sort of for the next state, and how does that affect performance?
Yeah, that's a good question. Right now, just to keep it simple, we basically only update the master state when the master branch has a successful run, and we just have this one version of it. We want to support it so that if you're making a lot of changes on the same branch, we could also have a snapshot for that specific branch. Yeah, and of course, there's performance trade-offs for this. We could try to update it less frequently, but then that would mean that the subsequent runs maybe aren't as fast because we're not getting the updated changes. So yeah, for our personal use, we're just going to experiment it and tweak it and see how things look.
I also have a question. I think it's check. Okay. I think it's quite common that people are still using Docker containers to insulate like a development environment, but that also means that people cannot just start using this way that you proposed with Firecracker. So the question is there an easy way to migrate quickly from Docker to Firecracker?
Yeah, so one of the reasons we chose Firecracker is that it's actually really easy to run a Docker container on Firecracker because a VM is essentially a full machine, so it's really easy to just run your Docker container there.
Yeah, I'm just not fully following how we can later access Bazel server if it's running inside of container, but I guess I should just try it out and see it myself.
It should look exactly how you're running Bazel in your Docker container currently. You're just moving it from whatever runner it was currently on into a Firecracker machine. Okay, cool. Thanks, everyone.
All right, thank you, Maggie. That was an awesome talk.